In general, a circuit simulator can perform DC simulation, time domain simulation, and frequency domain simulations. We have covered how to simulate circuits with an input source as the running variable, as well as how a circuit responds to time-varying signals. In this presentation, I will cover the approach to perform frequency domain simulations. To explain the concept and the procedures to perform such simulation, I will work through a circuit example. Most of the steps in this example have been covered in earlier presentations, which I will just directly refer to. After this example, I expect you will be able to apply the principle you learned here, together with the previous knowledge to construct systems of circuit equations to solve any circuit operations in the frequency domain. To begin with, let's start with a simple circuit with only linear time invariant elements as shown in the given figure. In this circuit, there are two resistors, R1, R2, and a constant current source, IC. The input to this circuit is a frequency varying signal represented by the signal source, Is. While it is more often to have a voltage source as the input, we use a current source in this example because its matrix stamp is simpler. After this example, you should be able to apply the same method to analyze circuits with an input voltage source easily. In the simulation, we want to find out how the node voltages and branch currents vary relative to the input signal source. If the modified nodal analysis is used, we are only solving for the node voltages. In this case, we can use the matrix stamp method to add the circuit elements into the circuit matrix. The resulting circuit matrix is shown here. We can find out the voltage of node 1 and node 2 by solving this matrix directly. As the circuit only contains linear elements, no iteration is necessary, and the matrix gives the solution directly. If we plot one of the voltages, say V1, versus the input signal current, we can get a linear relationship as shown in this figure. In the frequency domain simulation, we assume an infinite small time-varying signal Is is applied to the circuit, and we want to find out the amplitude and phase of the output signal at each node. That is, we want to find out the value of voltage at any node J normalized to the signal source Is, as shown in this equation. But the resulting quantity contains both the magnitude and phase information. In order to center the oscillating signals about zero, we first treat all DC sources as AC ground and set them to zero. Then, the output voltage as a function of input signal source will pass through the origin as shown in the figure here. In order to normalize the response with respect to the input signal source, we simply set the matrix entry of the signal source to 1. After that, the following matrix is obtained. Solving it will give the gain of the circuit at each node with respect to the normalized input signal. If all the circuit elements are time invariant, the output as a function of input signal frequency will just be a constant, as shown in the graph here. It is not very interesting. We will add some linear frequency-dependent elements, which are the capacitor and inductor as shown in the figure. As the Jacobian matrix represents the coefficient of the node voltage vectors to give the required branch currents, it contains the admittance instead of the conductance of the circuit elements, with the frequency-dependent component added. And the admittance of the resistor, capacitor, and inductors are given here. Treating them the same way as conductance, we obtain the following circuit matrix equation. We can then solve for all the node voltages to find out their responses at different frequency omega. In this example, there is one issue. As the frequency response covers DC, omega can be 0. The admittance of inductor then becomes infinity, and the matrix cannot be solved. It is coming from the fact that inductor is considered a short circuit in DC. It may be tempting to solve the problem by avoiding the point omega equal to 0. However, I will show you shortly that the DC point cannot be avoided. To solve the problem, we can rewrite the branch equation to add the branch current as a state variable explicitly. By rewriting I equal to 1 over j omega L times V as V equal to j omega L times I, we avoid the 1 over j omega term and convert it into j omega. And the branch equation in terms of both voltage and current becomes what is given here. It is the same as the Thevenin's equivalent circuit described earlier when inductor was first introduced. And the matrix entries of an inductor is thus given by what is shown here. After modifying the matrix stem of the inductor, the circuit matrix to be solved becomes what is shown here. In order to solve the short circuit problem of the inductor at DC, the circuit matrix is enlarged, leading to longer time to solve the equations. In reality, there will not be that many inductors in a circuit, and the time penalty is acceptable. In particular, no iteration is required in frequency domain simulations, and the matrix size may not be as important as in DC or time domain simulation. After adding the capacitor and inductor, we will further add a nonlinear circuit element, such as a diode. It is added between node 2 and ground, as shown in the figure. Let's assume the IV characteristics is given in this figure. In frequency domain simulation, we assume the operation is at very small signal range, of which the input is approaching 0. Over a small region, the function can be approximated by a straight line at the biasing point. It is equivalent to a resistor with the resistance given by 1 over the slope of the IV curve at the biasing point. To find out the value of the conductance, we have to find out the biasing point that determines the operation of the circuit. Once it is solved, the branch voltage will be known, and the conductance can be calculated. To do that, we have to construct the circuit matrix for DC simulation and solve for the biasing point first. When we are solving for the DC solution, we should avoid inconsistency between the matrix for the DC solution and the one for frequency domain simulation. Such inconsistency can arise, for example, due to the possible different implementations of the inductor. To do that, we will start with the matrix for frequency domain simulation and modify it to form the matrix for DC solution. We first remove the value 1 contributed by the signal source. Then, we put back all DC sources, together with the equivalent current source resulting from the nonlinear element as described in earlier presentations. The contribution of the nonlinear element is given in red, so that they are easy to recognize. After that, we add the conductance contributed by the nonlinear element into the Jacobian matrix for iteration. Finally, we set omega to 0, as we are solving for DC solution. All the state variables will be solved by iterations performed by the simulator. Once all the voltages are found, the conductance G can be calculated. After solving for the conductance G, the contributions of the nonlinear element besides G are removed. It is because the nonlinear element is linearized and replaced by a resistor. The value of G is now known and can be treated as a constant. We can then solve the AC matrix by removing the DC sources, add back the one for the input signal source, and allowing omega to vary as the independent variable. Using this matrix, we can obtain plots for the amplitude and phase of the state variables as a function of frequency. By including the inductor current as a state variable, its frequency response is also solved explicitly. I would like to point out that as the solution matrix for the frequency domain is linearized, there is no iteration needed and no convergence issue. If there is any convergence problem, it usually happens when solving for the DC operating point. A nonlinear circuit element like a diode may also contribute a nonlinear capacitor in addition to the nonlinear resistor. As explained in the implementation of nonlinear capacitor, the charge Q as a function of voltage V should be given to avoid charge conservation problem. Assuming the QV relationship of the nonlinear charge element is given in the figure. It can also be treated as linear element at the biasing point when the modulating signal is small enough. Therefore, after solving for the DC operating point, the nonlinear charge element can be treated as a linear capacitor with its capacitance given by the charge derivative at the biasing point. And a nonlinear element can be considered as a linear combination of a resistor and a capacitor in parallel. Without repeating the details, the procedure for frequency domain simulation is similar to what has been done before. First, we solve the DC operating point. The capacitor can be ignored in this case because it is considered as an open circuit with omega equal to 0. After solving for the DC operating point, the DC matrix is reverted back for frequency domain simulation by setting all DC-related sources to 0, putting the input of the signal source to 1, and adding the contribution of the linearized capacitor to the admittance matrix. The complete matrix to simulate the frequency response is given here. There are other cases, such as multi-terminal elements. I do not want to cover them one by one, as the process is quite straightforward after all the examples given. I will just provide a summary of the procedures to perform frequency domain simulations, which apply to most of the general cases. First, we construct the circuit matrix with all DC sources and resistive elements. The capacitive elements can be ignored by treating them as open circuit with omega equal to 0. The signal source can also be ignored at this time. Then, add the inductor with its Thevenin's equivalent circuit, but set omega equal to 0. After that, solve these matrix equations by iteration. Once the solution is found, calculate the conductance and capacitance of the nonlinear elements as the current and charge derivatives at the biasing point respectively. After the operating point solution is found, the linearized matrix is constructed, with the nonlinear elements replaced by the equivalent linear resistors and capacitors. Then set the values of the DC sources to 0, and replace the right-hand side of the matrix that represents the signal source to 1. Finally, add the frequency components contributed by the frequency-dependent elements. Once this matrix is constructed, the response of the state variables to the input source at different frequency can be solved directly without iteration.